Welcome to the deep dive. Our job here is pretty straightforward. You give us source material, could be articles, lectures, research papers, anything really, and we dig into it.
Yeah, we sift through it all to pull out the core insights, the stuff you really need to know. We cut through the noise for you.
And today, we're tackling a technical lecture someone shared with us. It's all about version control, and specifically focusing in on Git.
Right. So our goal, our mission for this deep dive is to get a solid handle on what version control actually is.
Okay.
And also, why systems like Git became so essential, not just handy. And then we'll touch on some fundamental Git concepts.
Got it. And the lecture seems to take us on a bit of a journey, right? From people trying to manage file changes manually.
Oh, yeah. The classic, slightly chaotic methods.
That sounds familiar. All the way to the much more sophisticated automated systems we rely on today, especially for collaboration.
Exactly. So let's start where the source does, with the basic definition. It says, version control is, and I'm quoting here, a system that records changes to a file or set of files over time so that you can recall specific versions later.
Okay, that makes sense. Recording changes, recalling versions. It feels like something people naturally try to do anyway, even without specific software.
Absolutely. The lecture points out these common everyday things people do, like, just saving multiple copies of the same file but with different names.
Ah, yes. The report final.docs, then report final v2.docs.
Then report really final.docs.
Inevitably followed by report final for real this times where .docs. We've all been there.
We definitely have. Or using cloud storage like Google Drive or OneDrive. They often have some built-in version history, which is, a step up.
And the simplest version of all, just hitting undo or redo in your software, that's like microversion control.
It is. Yeah. But as the lecture quickly shows, these manual ways, they hit limits pretty fast. It uses this scenario with a student, a myth, working on a coding assignment file, numbers.py.
Okay, so a myth. He's trying to be organized, saving versions like numbers1.py, numbers2.py, and so on. The latest one is just numbers.py.
Right. And then disaster strikes.
Yeah.
Right before the deadline, naturally. The latest version, numbers.py, just crashes. Serious error.
Oh, no. Typical. So, okay, first thought. Just revert. Go back to numbers10.py or whichever was the last known good one.
That fixes the crash, yes. But here's the tricky part the source highlights. What if that buggy numbers.py also had good stuff in it? Maybe a myth added some new features, fixed some other small bugs.
Oh, I see. So you can't just toss the whole thing. Now he has to manually compare the working numbers10.py with the broken numbers.py.
Yep. Line by line, figure out what the good changes were in the broken one.
And then carefully copy just those good bits.
And paste them into the older, stable numbers10.py.
Yeah.
Trying not to break anything else in the process.
Wow. That sounds incredibly tedious and, frankly, really easy to mess up and introduce new bugs.
It really is. And that's just one person, one file. Then a myth has another worry. What if his laptop dies, hard drive failure, poof, all those versions gone?
Yeah, good point. So the lecture suggests the obvious fix. Copy everything to cloud storage, OneDrive, Google Drive, something like that.
Which seems smart. Pros versions are safe, backed up offsite, accessible from anywhere.
Sounds good. But wait, there's a catch, isn't there? The lecture mentioned a downside, especially with that accessible from anywhere bit.
Exactly. Let's say a myth works on numbers.py in the university computer lab. Saves it, it syncs to the cloud.
Okay.
Then later, he works on the same file name, numbers.py, on his laptop at home. He makes different changes. He hasn't renamed it this time.
Ah, and then his laptop syncs.
Right. The cloud service sees two files named numbers.py. What does it do? It might overwrite one version with the other, or create confusing duplicates. Either way, work gets lost, or it's a huge mess to sort out.
So that manual naming thing, it just doesn't scale well, especially when you're working in different places?
Not really.
Yeah.
So looking back at a myth system, the multiple files, the cloud backup, it sort of mimics version control, right?
Yeah.
You can revert, you can manually compare and merge, you have remote storage.
Conceptually, yeah. The pieces are there.
But is it easy? Is it reliable? The lecture argues pretty strongly no. It needs immense discipline just for one person.
And then what happens when you add another person? The lecture brings in Banesh, right, for pair programming.
Exactly. Now, a myth's possibly imperfect naming system needs to be followed perfectly by Banesh too, consistently, across all files. by both people.
That sounds unlikely to work flawlessly for long.
Very unlikely. Plus, just seeing file names like numbersmith v3 fix.py doesn't tell you what changed inside. You lose that high-level view.
Okay, so how does the manual system try to solve that?
Well, the suggestion is to add a log file, a separate text file where Amit and Banesh manually write down notes.
Like, Amit changed function X at 3 p.m., Banesh added feature Y at 4 p.m.
Precisely. Just a running commentary so everyone knows what happened, who did it, and when.
Okay, so let's evaluate this whole evolved manual system. Named copies, cloud backup, manual log file. Does it, technically solve the core problem?
The lecture concedes that, yes, conceptually, it does. You can revert, you can compare, you can merge handfully, you have remote storage, you have a history log.
But feels pretty big here.
It is. Is it easy? No way. And the crucial point the source makes is about scaling. Add more people, 3, 4, 10, to this manual system.
And the chances of someone messing up just skyrocket, forgetting to rename, overwriting a file, missing a log entry.
Exactly. One mistake can corrupt the whole system for everyone. The conclusion is pretty clear.
The idea is right, but humans shouldn't be the ones managing it manually. It needs automation.
Precisely. Which leads us nicely into the history of actual automated version control systems, or VCS.
Okay, where did these start?
The lecture mentions the first generation, like the source code control system, SCCS Bell Labs, 1973.
Wow, 73. That's way back. So local VCS, what did that mean?
It meant it tracked changes to files, but only on your local machine. And really, only one person could safely edit a file at a time. Not great for teamwork.
Right. So what came next?
Second generation. Centralized VCS, think client server. There's one main central repository server holding the master copies of the files.
Okay. So multiple people connect to that central server over a network.
Yep. They check files out, work on them, check them back in. It allows concurrent work, which is a big step up for teams.
But you need that network connection, and someone has to maintain that central server, right? Like a single point of failure.
Exactly. Those were limitations. Especially as open source projects grew. With contributors scattered everywhere, relying on one central server became awkward, which led to the third generation.
Distributed VCS, which is where Git comes in.
That's the one, Distributed VCS or DVCS. It's more peer-to-peer in concept, meaning every user gets their own complete copy of the entire repository, history, and all.
Oh, wow. So you don't need to be connected to a central server all the time.
Correct. You can work offline, commit changes locally to your own copy. The whole system doesn't depend on one central point, and these DVCS systems are pretty much standard practice today.
And the big name, the one everyone seems to use now, according to the source, is Git.
Yep, Git, created by Linus Torvalds in 2005.
The Linux guy.
The very same.
And the source mentioned a fun fact about the name, the pronunciation.
Yeah, it's usually pronounced Git, like Git, but with a hard G.
Not shit.
Not usually, no. And Linus apparently joked he named it Git, which is British slang for like an unpleasant, incompetent person, referring to himself.
Okay, so it was built for the Linux kernel originally. That's a massive project.
Huge. So Git was designed from the ground up to handle that scale, support nonlinear development, basically. Lots of people working on different things in parallel, on what Git calls branches, and to be fully distributed.
Okay, let's get into some basic Git concepts from the lecture. He said it's distributed, but it can feel centralized sometimes.
It can, yeah. Because of how repositories are typically used, there are two main types. First, your local repository.
That's the one on my own computer, my personal copy of everything.
Right. You get it by, say, cloning it from somewhere else or starting a new project from scratch. It has the whole history, your changes you've pulled from others. You commit your work here totally independently.
Okay, and the second type?
The remote repository. Now, technically, in a pure distributed model, you could just connect to anyone else's local repo. But in practice,
That gets chaotic.
it can. So teams usually designate one or more repositories, often hosted somewhere accessible like GitHub or GitLab, as central points.
The single source of truth, the lecture mentioned.
Exactly that. This remote repo is where everyone agrees the main version of the project lives. You push your finished local changes to the remote to share them.
And you pull changes from the remote to get updates from everyone else.
Precisely. It solves that coordination problem.
Okay.
If everyone has their own copy, which one is the real one? The remote repo acts as that agreed-upon reference point.
Makes sense. And Git tracks everything using commits.
Yes, commits. Think of a commit as a snapshot. It's a record of the state of your project files at a particular moment, specifically the changes you decided to save.
And each one gets a unique ID.
A unique commit ID, yeah. It's generated using a hashing algorithm, SHA-1, based on the content and history. It's like a fingerprint for that exact state.
And the lecture mentioned head.
Head is just a pointer. It usually points to the very latest commit you've made or checked out on your current working branch. It tells Git where you are in the project history.
Okay, so the basic workflow. Let's walk through that again based on the source. I change a file.
Right. You modify files in your working directory, then you tell Git which changes you want to save. That's often called staging or adding.
Then I commit those stage changes to my local repository.
Correct. Now it's saved in your personal history. To share it or get updates first, you often pull from the remote repository. The lecture used the term upstream for that remote, right?
Yes, upstream. What does that signify exactly?
Upstream usually refers to the main remote repository you're tracking, the one you originally cloned from, or the one designated as the central hub for your team. It's where you push to and pull from.
Got it. So I pull from upstream.
Git fetches any new commits from there and tries to merge them into your local work.
And then I can push my local commits, including the merged updates, back up to that remote upstream repository.
Exactly. That shares your work with everyone else who uses that remote. Add file, change file, commit locally, pull from remote, push to remote. That's the core loop.
Okay, now let's circle back. How does this automated Git workflow compare to poor Myth's manual struggles?
It blows it out of the water, basically.
Yeah.
Remember a myth needing to find numbers 10.py to revert?
Yeah, digging through old files.
With Git, the source says you use a command like git revert and give it the commit ID you want to undo. Git then creates a new commit that reverses those specific changes, keeping the history intact and clear. No manual file hunting.
And the painful manual comparison and merging, copying and pasting between numbers 10.py and the buggy numbers.py.
Git handles merging automatically most of the time. It's really good at figuring out how to combine changes from different people or branches. You only need to intervene manually if there's a direct conflict, like if you and someone else change the exact same line of code in different ways.
Okay, that alone sounds like a huge win.
It is. And pulling changes from the remote location, instead of manually downloading and figuring out sync issues.
Git does it with a command, pulling down just the history and files you need.
Right, and pushing your changes back up to that safe remote storage.
Also, just a Git command automates the upload and sharing.
Yep. And finally, that manual log file a myth and Beanish needed?
Completely unnecessary, right? Because Git is the log file.
Exactly. Every commit automatically records who made the change, when they made it, the message they wrote explaining the change, and that unique commit ID. The entire detailed history is built in, automatic, and searchable.
So essentially, all those things a myth was trying to do, manually revert, merge, store remotely, log history, Git just does them reliably, automatically.
Right. And scales them up. It makes those processes robust enough for huge, complex projects with thousands of contributors, which the manual way could never handle.
So wrapping this up, the big takeaway is that these automated systems, like Git, aren't just conveniences. They fundamentally enable modern software development and collaboration.
Absolutely. They provide that safety net, easy reverts, reliable merging, clear history. It lets people experiment more freely, work in parallel effectively, and just build things faster and more confidently. It shifts the burden of version management from the error-prone human to the reliable machine.
It really changes the game. And thinking about that need for a single source of truth, that remote repository in Git that helps coordinate everyone's distributed copies, it makes you wonder, doesn't it?
And also,
Well, this problem Git solves managing and agreeing on the correct state of information when it exists in many different places and is constantly changing. How does that core challenge show up in other areas? Beyond just code. Think about news, scientific research, historical records, any complex system where information is distributed and needs verification and coordination. What can we learn from Git's approach to establishing that agreed-upon truth?